What if one of the most famous ideas in modern physics was actually wrong from the very beginning? What if Stephen Hawking, the man who told us black holes can die, had missed something so deep that Richard Feynman could have torn the whole theory apart with one simple question? Because here's the thing, Hawking's black hole equations changed physics forever. But Feynman's way of thinking about reality might have proved them incomplete. And the strangest part? Decades later, modern physics is finally catching up to what Feynman would have seen straight away. So let's slow this down and walk through it carefully, because the showdown between Feynman and Hawking isn't really about black holes. It's about the nature of information, reality, and whether the universe forgets. Now, picture Hawking back in 1974. He was working on something nobody believed was even possible. He combined Einstein's gravity with quantum mechanics right at the edge of a black hole, and out came this stunning result. Black holes aren't completely black. They glow, faintly, almost imperceptibly. They leak particles into space, slowly, over unimaginable spans of time. We call this Hawking radiation. And the implications were enormous. If a black hole radiates, it loses mass. If it loses mass, eventually, it disappears. But Hawking pushed it further. He said the radiation coming out is purely thermal, random, featureless, like static on an old TV. Which meant whatever fell into the black hole, a planet, a star, a library of every book ever written, would be gone, erased, forgotten by the universe. And this is where Hawking's idea hit a wall, because there's one rule in quantum mechanics that physicists treat almost like a sacred law. Information cannot be destroyed. Every quantum process, no matter how violent, must in principle be reversible. The past leaves fingerprints. Always. So if Hawking was right, then the universe wasn't reversible anymore. The whole foundation of quantum theory was cracking. And this is exactly where Feynman would have raised his hand. Now Feynman, if you don't know him, was the rebel of physics. He didn't trust complicated maths unless he could feel the picture behind it. He'd built huge parts of modern quantum theory with his bare hands, and his instincts were almost legendary. So the idea that information could just vanish, with no trace, would have struck him as more than a puzzle. It would have looked like a crack in reality itself. And he gave us one of the most beautiful tools in modern science, the path integral. Feynman's idea was simple but mind-bending. He said a particle doesn't take one path from A to B. It takes every possible path at once, and the universe sums them all up. Every history, every twist, every detour. Nothing is ever truly lost. Every option contributes to the final outcome. So when Hawking said information vanishes inside a black hole, Feynman's framework practically screamed back, that can't be right. Because if you can't track every history, the maths of quantum mechanics falls apart. So here's where the conflict really heats up. Hawking said the black hole eats the information. Feynman's framework said information must always be preserved. Hawking trusted general relativity at the event horizon. Feynman trusted the deeper rules of quantum mechanics. Hawking saw a one-way street. Feynman would have seen a network of paths all whispering back. Hawking believed gravity wins. Feynman believed quantum mechanics doesn't bend for anyone, not even a black hole. And honestly, if Feynman had lived long enough to fully tangle with this, he wouldn't have argued politely. He would have drawn a diagram. He would have asked, where did the path go? Show me. Because for Feynman, every particle in the universe has a story, and you can't just let the story disappear. And the disagreement runs even deeper than that. Hawking's calculation treated the radiation coming out of a black hole as perfectly thermal, meaning every photon escaping is just a blank, featureless particle, identical to the next. Feynman would have looked at that and said, hold on. Real particles in nature carry correlations. They're entangled, they remember. So if Hawking's radiation is truly featureless, then quantum mechanics has been lying to us for 100 years. And Feynman wasn't going to accept that. Not from anyone, not even from Hawking. But here's where it gets really strange. For decades, this paradox sat there, like a wound in physics. Hawking dug in. Other physicists started taking Feynman's side. The whole field split into two camps, those who believed Hawking and those who believed information must somehow escape. Then, in 1997, Hawking made a bet with another physicist. He bet that information really was lost. He stood by it for years. But the universe had other plans. Around 2004, Hawking, yes, the same Hawking, stood up at a conference and admitted he was wrong. He conceded the bet. He said information probably does come out of black holes after all. And the physics community sat there stunned, because in that moment, Feynman's deeper instinct had quietly won. Not because Feynman ever wrote a paper on Hawking radiation, but because the principles Feynman defended, unitarity, reversibility, every history mattering, turned out to be unbreakable, even by a black hole. Now think about this for a second. Feynman wasn't even alive to see it. He passed away in 1988. But his way of thinking, that the universe never forgets, outlasted him and reshaped one of the biggest debates in physics. And modern science has only gone further. There's now strong evidence from a tool called the ADS-CFT correspondence that black holes don't destroy information. It's a deep mathematical bridge that links the inside of a black hole to a quantum description on its surface, and it shows that nothing is ever truly lost. There's something called the page curve, which actually shows information leaking back out as the black hole evaporates, slow at first, then accelerating until every last bit comes home. And Hawking himself, in his final years, worked on a paper about soft hair on black holes, tiny imprints on the event horizon that might carry the memory of everything that fell in. Sound familiar? It's almost the picture Feynman would have sketched. Memory baked into the structure, nothing erased, every history leaving a trace. So where does this leave us today? Hawking gave us the most stunning result of 20th century black hole physics, that black holes glow, evaporate, and have a lifetime. That stands. That's not wrong. But on the deeper question, does the universe forget? Feynman's worldview won. Quantum mechanics held its ground. Information survives. The cosmos keeps the receipts. And maybe the strangest takeaway is this. Feynman didn't need to write the paper that proved Hawking wrong. His tools, his intuition, his stubborn belief that you must always be able to follow the path. It was already enough. Hawking saw the storm. Feynman saw the threads inside the storm. So now I want to leave you with this thought. If Feynman were sitting next to us today, looking at the latest data, what would he say? Would he smile and shrug? Or would he just lean forward with that grin of his and ask one more question, the kind that breaks open another century of physics? Because the truth is, the conversation between Feynman and Hawking isn't really finished. It's just waiting for the next mind brave enough to keep it going. And maybe that mind is yours.